Lesson 1.5, Infinite Geometric Series. So example number 1, they're saying, how much would you have if you were to be paid a penny on the first day, 2 pennies on the second day, and 4 pennies on the third day? And if this amount kept doubling every day, how much would you have after 30 days? So in this example right here, you want to start by finding out your R, which is 2, because that's doubling. And your T1, you start with 0.01 as to represent 1 penny. So once you have that, we're going to find out for 30 days, so the sum of 30 days, how much money would you have? So if I replace your T1 with 0.01, your R will be replaced with 2 to the power of 30, subtract 1 from there, and divide this whole thing by R minus 1. So if you were to calculate this, you're going to get that this is a large amount of money. This is over $10 million. So this is about $10,737,418.23. So that is a large amount of money if you started with 1 penny and kept doubling it every day for 30 days. So that's just a recap from our previous lesson. So example number 2 is what an infinite geometric series is all about. It's about a series or a sequence of numbers that continue on forever. So for example, 1/4, 1/2, 1/4, 1/8, 1/16, they're asking us to estimate what we think the sum is approaching. So in your calculator, if you put 1 divided by 5 plus 1/4 plus 1 divided by 4 plus 1 divided by 8 plus 1 divided by 16, we would get that the number is about 0.9375. And if we kept adding numbers, we would see that it starts to seem like it approaches 1 as a sum. So this means that it is convergent because it approaches an actual number. Our next number, if we were to keep adding numbers on, 0.5 plus 1 plus 2 plus 4, it would keep getting larger and larger and larger. So that means that the sum approaches positive infinity. And this is a case of a divergent series. So this doesn't approach an actual number. Our next one, if you start looking at these numbers, if you take 1/2 and subtract 1/4 and add 1/2 minus 1/16, you'll start to see that the number might approach 0.3. So this is again approximately convergent. So if our numbers approach an actual number, we can say it's convergent. If it approaches infinity or negative infinity, or go in both directions, we can say that it is divergent. So the formula that we're going to use if a series is convergent, to find the sum of infinite terms, we can take the first term and divide it by 1 minus our common ratio. So example number 3, they're giving us a series where T1 is 4, T2 is 2, and so on. So as you can see, the numbers, we keep adding a smaller and smaller number to it. Eventually, it's going to approach a fixed number. The addition of them is going to approach a fixed number. So that means this is convergent. So we can find the sum. So it says the partial sum is a fixed value of. So if we were to add this together, it seems like it adds up to, I would say it's like 7.75, right? So we can say that it seems to be approaching the value of 8. It's convergent. So that's just by adding them. That's the partial sum. It's not the actual sum. We would have to use that formula to get the infinite sum. This one, the numbers are increasing higher and higher and higher. So that means the sum would be approaching positive infinity. So this is divergent. And they're saying determine whether each infinite geometric series converges or diverges. If it diverges, determine the sum. Well, this first one, as you can see, the positive numbers go down and the negatives go up, which means that they're going to meet somewhere, and that means it's convergent. So if the two kinds of sums approach each other, the negatives approach the positive ones, it's convergent. So we can use the formula for sum of infinite numbers, which is 27, your first term, divided by 1 minus your r value. Our r value can be found by taking negative 9 and dividing it by 27. That simplifies to negative 1/3. So if you put this into your calculator, you're going to get 20.25 as the sum that it approaches. Our next case, if you look at it, the positive numbers increase and the negative ones decrease. So this means that it is divergent. It's never going to approach an actual sum, constant value. The sum is not going to approach a constant value. Here, if we keep adding a smaller fraction, this is going to be convergent. So anytime we add a smaller and smaller number, it's going to be convergent, which will take t1, which is 1, and divide it by 1 minus your r value, which is 1/5. That's by taking t2 divided by t1. If you put that into your calculator, you'll get 1.25 as the sum of infinite terms. Here, the numbers keep increasing, which means that the sum is going to approach positive infinity, and so that is a divergent case, which we do not calculate the infinite sum for. Example number 7, we're trying to write a fraction that would represent this number, so I'll show you how that's created. So our ratio is always taking the second term and dividing it by the previous term. So that's going to give us 0.001. T1 is going to be 0.584. So we're finding this infinite sum of 0.584 divided by 1 minus 0.001. So that, if you write it, if you put that into your calculator at the bottom, it's going to give you 0.999. As a fraction, if you move 3 spots to the right, it's going to be 584 over 999, and that's going to be the sum of the series. So that's the exact answer that gives us the sum of the series. Now, what if we have this one right here, where we have 0.49 repeating, where if you look, only the 9 is being repeated. So that would be equal to 0.4 plus 0.09 plus 0.009 plus 0.0009 if we were to break it up, and it continues on forever. So if you were to look at the common ratio between the first and the second term, we would get that if you divide 0.09 divided by 0.4, you'll get 0. Oops. Let's go back. So over here you would get 0.225 as the common ratio, versus between the third term and the second term, if you divide these two, you're going to get 0.1. And then again, if you divide these two, 0.1. So it's only really a geometric sequence from term 2 and on. So what we're going to do is we're going to only look at the sum of the infinite terms from this point of 0.09 and above. And so the 0.4 we're going to ignore for the time being. So the sum of infinite terms, we're going to use 0.09 as t1 divided by 1 minus your r value is 0.1. So as a fraction, that's going to be 0.09 over 1 minus 0.9. So if you move the decimals over, it's going to be the same as saying 9 over 90, which simplifies to 1 over 10. So with this answer, we're going to take 1 over 10 and add it with 0.4. So that way we get the sum of the entire sequence. So common denominators means we're going to have to multiply this by 10 and the bottom by 10. So that's going to give us 1 over 10 plus 4 over 10, which is 5 over 10, and that simplifies to 1/2. So that is the actual fraction that is equal to 0.4999 repeating, is what they're saying. Our exit task is where our T1 is 1, our R is 0.5, and we're just finding the sum of the infinite terms for this given geometric series. So this one does exist because it is convergent. We're adding a smaller number to get to each time as we go through the sequence. So 1.01 minus 0.5, so 1 minus R. If you put that into your calculator, you're going to get 2 as your sum of your infinite geometric series. So that is the last example. I hope you guys